In this video, what I want to do is do some chapter 8 examples. And so what I have is I have a single problem that has a few different pieces to it, and each piece kind of belongs to a different section of chapter 8. So what's going to happen here is we have a physician who's trying to determine a patient's mean systolic blood pressure. The systolic is the higher number, so like it's the 120 of the 120 over 80. It's measured in millimeters of mercury. And the physician has the patient take their blood pressure at the same time every week for 12 weeks. So say like Monday at noon, something like that, just something systematic. And then what they do is they record the systolic blood pressures. And so what we want to do is we want to find a 95% confidence interval for the patient's mean systolic blood pressure, assuming that we have a standard deviation of 3, again, millimeters mercury. And so what we're going to do, if we have the standard deviation, this becomes a 8.2 problem. And so the confidence interval is going to end up being the mean value of our sample, which we'll figure out what that is, plus or minus z sub alpha over 2, where our alpha, if it's a 95% confidence interval, our alpha is 0.05 because our 1 minus alpha is 0.95. So it's a 95% confidence interval. So that means that we have a 0.95 confidence or 0.05 significance. And then that's going to be multiplied by the population standard deviation divided by the square root of the number of data points that we have, which in our case will be 12. So our confidence interval is going to be the mean, which we'll figure out what that is in a second, plus or minus this value. And so what we're going to get for us, and what I want to do is jump over to R, and I want to show you how I kind of use some of the tricks of R to get R to give this very nicely. Let's say I want to find the confidence interval to 2 decimal places, so I'll show you how to do that using R. And again, it's nothing that we don't know, but I just want to do this. So what I have already is I stored our data set. So that's the 133, 128, 117, 133, 141, 139, 119, 125, 123, 132, 126, 116. Good. So that's our data set X. I always just like to make sure that I didn't miss anything. There are 12 numbers there, so that's good. And then we want to find a 95% confidence interval. Now there's no built-in function in R for this, but what I like to do is I like to let E, capital E, denote the error. And what the error is going to be is it's going to be the z sub alpha over 2 times sigma over square root of n. Our z sub alpha over 2 is Q norm 0.975. So let's just talk about that for a second. And then times 3 divided by square root of 12. So, because that times sigma divided by square root of n. So the Q norm of 0.975, remember what's happening is that z sub alpha over 2 is the cutoff where the area of the region to the right of it is alpha over 2. If our alpha is 0.05, then alpha over 2 is 0.025. And so that means that we're looking for the place where the cumulative probability is 0.975. Okay, so all that together gives us our error E. And I like to just call that E for error. And then what we're going to do is I'm going to let M be the mean. And then our mean of the data set is going to be 127.67 basically. And then what we're going to do is we want to find the confidence interval. So we're going to take the mean minus the error and then the mean plus the error. So there's 2 ways that we can kind of record the answer. And I think it'll be useful to have both of these here. It'll be nice just to have the error. And so in fact, what I want to do is let's round the error to 2 decimal places, and it's 1.70. But we could also use the following code to get it to give us a list here. So what this is going to do is it's going to give us a list of 2 numbers. The first number is going to be the mean minus the error. The second number is going to be the mean plus the error. And then there's our confidence interval. And again, if you wanted to be super fancy pants, you could do, you could round this to 2 decimal places. And there's the confidence interval to 2 decimal places. So let's go back and we'll record this. Okay, so we'll write this down. So I'm going to add this to the worksheet that we have here. Come on, Zoom. There we go. So our alpha was 0.05, z sub 0.025 was 1.96 more or less, so that's what we found. So that's what you would find if you had the table. Our sigma was 3, our square root of n was square root of 12. So this turns out to be the mean, which is 126.67 plus or minus 1.70. That's what we found when we did this in R. And so if we want to write that as an interval, we could also write this as the interval from 125.97 to 129.36. And I think what's going to happen here, just to mention this, is that I rounded this 126.67 first. I think R rounded it second, so this might be slightly different. We might be off by a hundredths place here, but that's how we do that with R. So that's number one. Number two says same setup, and what we want to do is, before we had a standard error of 1.7, what I want to know is how many times would we have to have the patient take their blood pressure if we want to make sure that that error is 1 or less. So what's the minimum number of measurements that we need to have? And so for this, what we're going to use is, there's two ways to do this. You can either think of the error formula. So the error is going to be z sub alpha over 2 times sigma over square root of n, or solving for n, which we did in a previous video. N is going to become z sub alpha over 2 times the error, times sigma over the error. So times sigma over the error. So squared, all quantity squared to get rid of that square root. And so what we're going to do is we'll just plug everything in. So n is going to be, let's jump over to R again. So we're going to have basically 1.96 times 3 all over 1, which is what we wanted. Okay, and then we're going to square that. Let's plug all this into R. So I'm going to do Q norm of 0.975 all times 3. Let me actually show you what this is going to look like. Again, nothing too surprising about what I'm typing, but it's going to be more useful if you can also see it. So this is going to be Q norm of 0.975 times 3. And then I'm not going to, you can divide by 1 if you like, but, and then we're just going to square it. So it turns out that this number is 34.573. And what I want to do is I want to point out that this is not an integer. So what we really need is we need 35 measurements. There's no way to get the error to be exactly 1. But going from 34 to 35 measurements is where it crosses over 1. So if we have 34 measurements, the error is going to be a little bit larger than 1. And if we have 35 measurements, the error will be a little bit less than 1. So if we want a standard error of 1 or smaller, we need to have 35 measurements. Okay, and that's how we will do that one. Okay, so that's how that's going to work. All right, so our final step, let's go back and I'll show you the final question, is going to be basically over the same premise. We're going to have a systolic blood pressure. It's going to be using the same data that we had before, except this time we want to find a 95% confidence interval, and we're not assuming that we know the patient's, the standard deviation of the systolic blood pressure. If we don't know the standard deviation of the underlying population, this is going to be a t-test. And so what we can do simply, and I just love this function in R, but what we can do simply is just go back and use the t.test function. The t.test function is actually more powerful than what we need right now. There's a lot of stuff that we're going to just ignore. So ignore the t value, ignore the p value, ignore, we'll talk in the next section about what even is an alternative hypothesis. But really the key information for us is the 95% confidence interval. Okay, so that's going to be useful for us. So our confidence interval is going to be, let's make this blue. So our confidence interval is going to end up being the interval from 122.4601 to 132.8733. And I guess just to be consistent with myself, let's round to 2 decimal places, which in our case is going to make it 122.46 to 132.87. Or you can write it as the mean plus or minus the error, where the mean is 127.67 plus or minus the error, and the error is going to be whatever that is. So it looks like it's going to be 5.20. Okay, so I'm just doing that with arithmetic. Don't trust me, never trust me. But you could figure out this error here. So that error is going to end up being t sub alpha over 2 times s, which is our standard deviation of the sample, divided by square root of 12. Okay, so we could figure out what that is as we go along. So that's it. So that's the example. I think that this is enough to get us through chapter 8.